Hello guys. Anyone? Can you hear me? Can you see me? And can you see the screen?
Yes, sir. Good morning, sir. You can see, sir.
Right, thank you. Thank you for the response. Okay, let's just take a moment to scan attendance and then we shall begin again our class today. All right, let's start with our class again today. All right, good morning, everybody. How are you doing? How's everyone doing in your own place? Hopefully, you're doing fine. Yeah, we have had a long week without class. Actually, I wasn't aware that Tuesday was a holiday last Tuesday, so I was expecting to teach last Tuesday, and then one of my friend actually told me that Tuesday is a holiday, and I remember that hey, if that's the case, then we have class on Tuesday. I was really thinking to have a class on Tuesday or not, but I've decided not to because everyone is, I mean, everyone has a right to enjoy the holiday, right? So I don't want to crash anybody's holiday by conducting classes on a Tuesday. So that's why on Tuesday we didn't have class and we could not have class actually on Tuesday. All right. So hopefully with one, I think it's 1 week, right? Yeah, the last time we had class was 1 week ago. So hopefully within this 1 week you've had a lot of time to finish your assignment. Also had a lot some time to finish your quiz. And I also do hope that you guys will spend some time to take a break, take a rest also sometimes, right? Because I know right now is the middle of the semester or something, almost the middle of the semester. Maybe like schedules getting hectic, like more and more assignments piling up. So do remember to take yourself a break sometimes. We all need breaks. Like even I too. I need breaks too. All right. So as usual, I'm extending my help to anyone out there who's facing any kind of problem. So especially problem related to the class. So if you have any problem with your quizzes, with your assignments, once again, I'm extending my help because this is the value that I can provide to you guys by being in my class, but it's my tutoring to you because this is what the tuition fees you're paying for actually. So please make use of this, like, right? So otherwise, um, the materials they are all out there, right? So they're all free. They're all on the internet and everything. But the one thing that they don't have is the tutoring, the guidance. So which is what I'm here to do, and I really hope that I can do a good job for this because I know you guys are not paying cheap. You guys are not paying a small amounts for this for this class. All right. So once again, I'm extending my help to anyone out there who's facing any kind of issue with this subject, any kind of technical topics that you don't understand, quizzes, assignments, whatever that's related to digital logic. All right. All right. So apart from that, I'm also open to talk to you if you have any issues other than the class, right? So let's say you have some kind of issues where you cannot cope with the class. I'm open to talk to you. I'm open. If I can help, I will do my best to help. If you don't have any device, I can use my resources as well. I can forward your case to the people in charge to get you a device or something like that. I think some of you have reached out to me. Yeah, of course, I cannot guarantee because these are not my decisions. The best I can do is to forward your case. And of course, if you think that you are suffering from any other kind of problem, don't suffer silently, guys, because it's so easy to do so. Especially right now, mental health. Mental health is so important, guys. mental health. If you don't look after mental health, like it can eat us from within. Like, so I realized that especially guys, like I mean talking about males, like we don't tend to talk a lot about this stuff. So it's like all of a sudden, boom, then something happened. And then like before we know it, oh, that person so and so, like he was suffering from a mental breakdown or something like that. So if you're suffering from any kind of, if you're feeling stressed, you're feeling depressed or something, right? Just to let you guys know, my doors are open. Like if you think I can help you with anyone or anything of this, please reach out to me. Okay. So if you don't wanna reach out to me through a voice call or something, like you can always text me, you can always email me, or just do whatever to reach out to me. All right. All right. So just a little note there, because this is a serious issue actually during this pandemic. I think I'm not sure if you guys realized it. Okay. So let's get back to our class today. So actually last week we have finished one of the most central topic in digital logic, and that is topic 4. So in topic 4, what we did was we did Boolean laws, Boolean algebra laws in the beginning, and then after that we learned about simplification of Boolean algebra using Boolean algebra laws. And what that gives you is the power to simplify any equation using Boolean laws. And on top of that, we also on the second part of the topic, we also did simplification using a tool called K-map. So now you have at your disposal two tools that allows you to build any kind of system. I'm not sure if you guys realize it or not. So if you have any system that consists of inputs and outputs, right? You can construct the truth table. Once you got the truth table, you can use K-map, or you can use Boolean algebra laws to simplify the table, and then you can build the circuit using logic gates, right? So this is a skill, and this is something that is valuable that I think that you guys can learn from this class, all right? And in this chapter 5, it will be a little bit continuation from chapter 4, from topic 4, and in topic 5 we are going to talk about combinatorial logic. Okay, so basic combinatorial logic. Okay, some in some books or online they don't use this combinatorial. This word is kind of strange. They use this word combinational. Okay, so this is one keyword that you want to remember if you are doing any self-study on your own. Combinational logic, combinatorial logic. Okay, but I'm gonna stick with this combinatorial logic because this is the term that I use throughout all my slides, but it's the same thing. Okay, so basic combinational logic, combinatorial logic. So combinatorial logic is very simple. So it only consists of 2 or more logic gates. So what that means is that all this while you guys are already doing this combinatorial logic, but you just didn't know this term exists. Okay, so in any system that consists of 2 or more logic gates, it's also known as a combinatorial logic system. Okay, so one thing to remember is that um, in any combinatorial logic system, it's got no memory. Okay, it's got no memory. So what do I mean by it's got no memory? So let's suppose you have a system, right? You have a system. System consists of 3 inputs, A, B, C, 3 inputs, and then like you have output F, right? So if you give a value of 0, 0, 0, for example, and then the system outputs you, I don't know, maybe 1. Yeah, this is right now. You give it input 0, 0, 0, and it gives you 1. Let's say after 1 hour, you give a different kind of input. You give a 0, 1, 0 as the input, and then the system gives you output of 0. So what does it mean by no memory? So no memory means that it does not remember what is the previous input you give it. Okay, so it does not remember, like currently the input that you are giving is 0, 1, 0, right? It does not remember that previously you gave this input. Okay, so it turns out there is a system that can have memory as well. Okay, but it's not combinatorial logic. It's called sequential logic, and that is what we are going to learn in the next in topic 7 and topic 8. of this course. Okay, but we're not there yet. So we are just at this part. Combinatorial logic has no memory. Okay, right. So that is memory. Okay. So these are the styles of combinational logic circuits. So these are a few patterns that you can see. So I think it's quite self-explanatory over here. So we have AND OR logic, and OR invert logic, OR AND logic, or an invert logic. Okay, so what does this AND OR logic mean? This is the gate level. So the first one is the AND gate, and then it goes through an OR gate, and so on and so forth. Okay, so invert means you know that it's kind of a NOT gate, and this third one is the reverse. Okay, let's take a look at that. Okay, so AND OR logic. So AND OR logic directly implements the sum or product expression, assuming the complement if any. Okay, so if you take a look at any sum or product expression, like for example here. Okay, so for sum or product, the circuit would look like what you're seeing on the screen right now. Okay, so the circuit consists of, if you break this down into this kind of level from left to right, or yeah, from left to right, you would see that if you give it any input, this input will go through AND gate first, and then after that it goes through the OR gate. Okay, so it goes through the input. In fact, all inputs over here go through an AND gate first, and then it goes through an OR gate. The signal, the flow of the signal. Okay, so that's why you can see that this is a AND OR circuit. Okay, so an AND OR circuit directly implements this sum of product expression. Okay, so that is an OR circuit. The same thing we can see, it's, let's say this is the second pattern that you would have. So this is the AND OR invert. So same concept applies over here. So we have AND gate, and then the signal goes pass through this OR gate, and then it passed through a NOT gate at the end. Okay. So this kind of AND OR invert can be achieved with a POS expression. Okay. So if you look at the output of this expression over here, this is the original output is this, right? AB, CD, and then you have a big bar because there's an inversion going on. But if you break this down, you would get this. So guess what we use to break this down? Yeah, remember every time we have a big bar above, like we're going to use De Morgan's to break this down. So if you break this down, you'll find that it comes down to this, and this is a post expression. Okay, so AND OR invert logic, you can implement a post expression. Right. So the other way around, now we're going the opposite. Instead of AND OR, we now have OR AND. So OR AND is a product of some expression. Okay, so you can see over here, it's a product of some expression. It goes through OR gate first, and then the signal passes through an AND gate at the second stage. All right. So if we have an invert at the end, so an invert at the end is, so it goes to an OR gate, and then goes through an AND gate, and then it goes through a NOT gate. And at the end of the day, you would get this. Then if you break this down, you would get an expression also. Okay, so yeah, you get an SOP expression. All right, so those are four types of patterns that you would see in combinatorial logic. So right now, I want to also talk a little bit about levels of logic. So this is just a simple term that we use to describe the largest number of gates a signal must pass through from the input to the output. Okay, this is something that I've done also just now. So if you imagine you have a system, so you want to know the system has how many levels of logic. Okay, so for example, we have a system like below here. So this below system has 3 levels of logic. Okay, 3 levels. Why do I say you have 3 levels of logic? Yeah, because the number of level is calculated with the largest number of gates the signal needs to pass through. Okay, let's take a look at the first signal over here. So this, if you provide a signal over here, you can imagine this signal travels through this gate. There's one gate, and then it travels through the second gate. There's a second gate, and then it goes to the output. So this signal W here travels two gates. Okay, so you can imagine like a signal like going through like multiple gates, like multiple buildings, right? So same thing. So over here, if your signal over here, the same thing to it. But if you take this signal over here, you go through more than that. Right? So it's going through one gate, two gates, and finally you arrive at the output. So we have a signal that goes through two gates, and we have a signal that goes through three gates. So but we want to select the level that is the largest number of gates. Okay, so for this particular system, we have three levels. Right, so that is levels of logic. Quite straightforward. All right, so this is the meat of today's class. So I want everyone to pay close attention to what we are going to cover today. Yep. So remember we talked about universal gates like before this. I'm not sure if you guys remember that I talked about universal gates, but we didn't go through in detail what in the world is actually a universal gate and why is it called a universal gate. So there are two of them, two universal gates. One is NAND, the other one is NOR gate, right? So in today's class, I'm going to show you how you can use NAND gates to construct any gates. That's right. You can use NAND gates to construct any other gates, any other system, any. So you can imagine this NAND gate is like a Lego block that you can use to construct any system. So that's why it's called universal gate, and the same applies to NOR gate as well. So this is what I'm showing you on the slides over here. Is anyone typing in the chat? I see some notification over here. Okay, no, nothing. All right. So if you guys any question, you can just type in the chat. I am constantly monitoring the chat for things also. Okay, let's get back to NAND gates. So we want to see what's the property of NAND gates over here we have. So as I said just now, using NAND gates, we can construct any other gates. Yes, that's right. So what we are seeing over here, let's take a look at this first case, right? First case, we are seeing NAND gate over here. This guy is NAND gate. Okay, so what we are doing over here is we are using NAND to construct a NOT gate. So how is that possible, right? So this is how it's possible. If you take a NAND gate and you connect two of the input, you would actually produce a NOT gate. So why do I say that? If you don't believe me, we can try it out. Okay, so we can try it out. We can simulate this thing to see what's the input and what's the output. So let's say you have A as the input and you have X as the output. Okay, so if you give an A equals to 0, so let's see what is X. A equals to 0, and then you can see that X is equal to. So if you put a 0 over here, you get 0. They're both 0. 0 and 0 is 0, and then you invert it, you get 1. Okay, that is the case of A0. What about A equals to 1? So if you change this, A equals to 1, you got 1 and the 1, you get 1, and then you invert it, you get 0. Okay, so this is what we have here. Okay, so this is what we have here. When A is 0, X equals to 1. When A is 1, the X output is 0. So isn't this the behavior of a NOT gate? Yes, indeed it is. So this is how we can use NAND to construct a NOT gate. Okay, the trick is simple. It's just connecting the two inputs. And there you go. You have a NAND gate that behaves exactly like a NOT gate. All right. So the same thing we can do for other gates. So let's take a look at this second example over here. So you have two NAND gates over here like this. But if you connect it in this way, it produces the behavior of AND gate. Okay, so we can try that as well. So you have A, B, and let's say X. You guys remember the truth table for AND gates, right? So let's try to simulate this. A, B, and X over here. So let's try to simulate this and see what we get. So we have 0, 0 over here. 0, 0, you get a 1, and then you get a 1 over here. So 1, 1, then you invert it, you get a 0. So you get a 0 like that, like this. All right. Now let's try the next output. The 0, 1. So you have 0 and 1 over here. 0 and 1. So you get 0. 0 and 1, you get a 0. And then you invert it, you get a 1. And then same thing over here, you get 1 and 1. 1 and 1, you get 1. You invert it, you get a 0. So which means over here, you also get a 0. And then you go, let's go to the next row. So in the next row, we have 1, 0. Okay, 0, 1, 1, 0, you get the same thing. So you get the output over here. So you can try it if you don't believe me. And finally, you get 1, 1, 1, 1. So let's try this. 1 and 1, you get 1, and then you invert it, get a 0 at the output. So you have 0 and 0. Invert it, you get 1. So this is the output we get from these two NAND gates over here. And if you haven't realized this already, this is the exact truth table of the AND gate. Okay. So what we've done so far is using only NAND gates, NAND gates, NAND gates. And in using NAND gates, we were able to construct a NOT gate, we were able to construct the AND gate. And if you dive deeper, you're also able to construct an OR gate. You're able to construct even a NOR gate, right? Using universal gate, you can construct another universal gate, okay? That's kind of mind-blowing. So conclusion over here. What's conclusion? Conclusion over here is NAND gate has got this universal property. So the reason it's called a universal property is, as I have told you previously, it's because using NAND gates, we can construct any other system you can imagine. Because it can already construct this basic logic gates, and NOT and OR. And using these three logic gates, you can construct any system, right? So that is the universal property of NAND gates. Okay, so far, any question on NAND gates? So far, so good. Can you guys understand what I'm trying to say over here? Okay, if there's no question, let me just continue. All right, the same thing we can do with, this time with NOR gates. Okay, so using NOR gates, we can also construct any other gates. Okay, so NAND and NOR, they're kind of like a partner in crime. So they are both universal gates. So the same thing we can do. Using NOR gates, we can also construct this NOT gate over here. We can also construct OR gate. We can also construct AND gate. We can also construct NAND gate. Okay, so this is how you wire it together to construct each of these respective gates. And that is why the NAND gates and NOR gates, they are called, they have this universal property. Okay, right. So then you might say that, oh, okay, so what is the purpose of using this universal property? Okay, for example, if I were to use an OR gate over here, it's this, it's one gate, right? It's one gate. But if I were to use NOR gates, this like two gates over here, right? So what's the use of, you know, using two gates when I can use one gate? So that is the kind of question that I have also in the beginning. But if you really think about it, when you are in a mass production scale, right? So when you want to produce a gate, when you want to produce an OR gate, so you need a machine to produce the OR gate, and you need a machine to produce the NOT gate. You need a machine to produce a AND gate. So if your system has got these three different gates, so your factory will need to have like these three machines to produce these three respective gates. But if your system only consists of one gate, all you need is a machine, a device to produce that one gate. And then you can use that one gate to construct any other system. So this is the advantage of using universal gates, in the sense that the production, the machine to produce to 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 produce this gate, like, it's only one, compared to you have multiple machines. You can think about it that, like, there's raw materials. Like, to construct something, you have raw materials that there's only one raw material, or there's like many raw material. So if you have many raw material, of course you gotta find ways to get this many raw materials into construct your system. But if your system only needs one raw material, so that can simplify a lot of things, and that can also lead to cost saving as well, right? But we'll not dive into like the cost and everything. But this is the property of universal gates that makes it uh, so it makes it advantageous compared to using many gates in the system. Okay. All right. So that's the universal property of NAND gates and NOR gates. So next we are going to take a look at so yeah, we're going to dive into a couple of examples, and then we'll end today's class. Okay. Right. Let's take a look at the NAND network. So if you want to implement anything in the NAND gates, okay, using NAND gates, so it requires that your function to be in the SOP form. Okay. So if you remember, this is how NAND gate looks like. Okay. That's A, that's B, and that's X. So X is A, B. So this is the pattern that we want in our system. There's two variables multiplying together, and you have like a bar across the two variable. So this is what we want to see in our system. This is the example, right? So suppose we have a system like this. Suppose we have a system like this. Now we want to implement this system. Let's just try to do this with normal gate, right? So this is the normal implementation. Okay, this is A, B, and you have like C, D, and they both have an AND gate, and then after that they go through OR gate. Okay, and this is F. Okay, but how do you want to implement this? Let's say you work in a factory production, and this is like a giant system. This giant system consists of few million AND gates, few million AND gates, and few million OR gates. So you want to simplify the system. Everything just use NAND gates, so that you don't have to source from multiple raw materials, right? So what we want to do is to convert this into this expression. Okay, why this expression? You see that this expression over here has the pattern that we want, right? So the pattern that we're looking for is two variables multiplying together, and then you have a bar on top, like two variables multiplying together, and then you have a bar on top. Over here also we have two variables multiplying together, and we have a bar on top. And if you look at the bigger one, we have also two variables multiplying together, and we have a bar on top like that. So if you have this kind of pattern, then you can use NAND gates. But then how exactly you know that this is actually equal to this? Exactly, De Morgan's theorem. If you break this down using De Morgan's theorem, you would find that it's equals to the simplified form. Okay, to the simplified form. So I leave that as an exercise to you guys. So run De Morgan's theorem on this, and then you'll get this one. All right. So key point that I'm trying to convey over here is the pattern that we are looking for is this equations, this pattern in the equations. I'm going to show you guys after this how do you get this pattern. Okay, so of course you can use the Morgan theorem to get this pattern if you want, but you can also use another tool that I'm going to show you after this. Okay, so next, yeah, this is the real question over here. So if I have the circuit like before, just now I was showing you, how in the world do you make it a NAND circuit? You have a circuit that has OR gates, that has AND gates. You want to make it into a NAND. So this is how it's going to be done. We can convert that circuit using, there's two ways. One is using De Morgan's theorem. So if you run De Morgan's theorem, you can get from here to here, okay, and the other way around as well. And the other way to do it is conversion by diagram. Okay, conversion by diagram. So this is what I'm going to teach you guys today. So before that, recall that a NAND gate is equivalent to invert OR gate. Okay, so remember this diagram. So if you have two gates, this gate on the left, this is NAND gate, and you have another gate over here is an invert OR gate. Invert means you have a NOT gate before. So this on the left is equivalent to this on the right. So why is it equivalent? Because the truth table is the same. So truth table is the same. And if you take a look at this, if you do De Morgan's theorem on this on the left over here, you would get exactly this equation. Okay, so that's why they are equivalent. Truth table points to the same thing, and the expression also is equivalent if you run De Morgan's theorem. Okay, so with this in mind, let's take a look at how we do it. Okay, so these are the steps that that is required for you to convert NAND by diagram, right? So we are doing by diagram now, not by De Morgan's theorem. I believe we did a De Morgan's theorem. Maybe we'll go through one example on De Morgan's theorem if we can after this. Okay, let's go through step by step on how do we convert any diagram, any logic gates to NAND by using the diagram alone. Okay, so first we want to convert the AND gates to NAND gates, and then we want to convert the OR gates to the NAND gates. Okay, and then like we want to check all the bubbles in the diagram. Okay, so this might look very vague to you right now. Let's dive into an example, right? Okay, so let's suppose this is the circuit that we're talking about. So the original circuit uses this AND gates, this OR gates, this AND gate over here, and there's multiple AND gates and OR gates over here. So the first step is to draw this original gate, and then we'll do the conversion. Let's draw this out real quick. So we have an AND gate. We have an AND gate. So we have A, B bar, and then we have an A bar. We have B. A, B bar, A bar, B. Okay, and then they add up. They add up. Okay, they add up over here, and then it goes through another AND gate over here in the center, and you have a C, D. Okay, let's do the C, D. Have C, D over here, C or with D, and then you want to take the output, and you want to run the output through the gate. Okay, so this is the circuit. Okay, let's just double check this circuit real quick. AB, okay, OR gate, AB, AND gate, and then they're all together. Then produce the output goes to an AND gate, CD, C OR gate, goes to the AND gate. Okay, all right, looks correct to me. Now we have AND gates, we have OR gates. So the real question now, how do you want to convert it using, if you want the circuit to only use NAND gates? Okay, here's how. Pay close attention to this, guys. This is the meat of today's class. All right. So what I want to do now for the first step is to convert the AND gates first. Okay, convert the AND gates first. Okay, so we want to start converting all the AND gates. So let's start from this first AND gate. So for this is an AND gate. How do you convert this into a NAND gate, right? It's very simple. All you got to do is put one little bubble here. And this becomes an AND gate already. Okay, now there comes the next question. If I do this, right, I'm changing the system's behavior, correct? I'm changing the system behavior. I cannot just put one bubble over here. So what I can do, if I want to put one bubble over here, what I can do is put another bubble over here. And in this case, am I changing the system's behavior? I am not changing the system behavior. Why? Because remember, a bubble is an inversion. So if I have one bubble, I invert once, and I invert another one time. Like one, it's like putting two NOT gates like back to back like this. Okay, two NOT gates back to back like this. So am I changing anything? Because one NOT gate would just essentially cancel the other NOT gates output, right? So if you put two NOT gates together, it's equals to not putting anything at all, because these two NOT gates just cancel one another. So that is what we are doing over here. Okay, so if you have if you have like this, yeah, these two, they are equal. So if you a equals 0 here, so you have a 0 here. It's the same thing as not having any gates at all. So that is what we are doing in this diagram over here. We are putting two NOT gates back to back to one another so that we do not change the behavior of the system. Okay, so I'm doing this over here. All right, so then can I do the same for this? Yeah, I can do the same for this guy. Okay, so then what we have over here is this one is a not, this one becomes a NAND gate already. This one becomes a NAND gate already. What about this? Okay, remember what this gate is about? This is a negative OR gate. What is negative OR gate? Negative OR gate. Negative OR gate is equivalent to a NAND gate, right? It's like magic. Negative OR gate is equivalent to a NAND gate. So what we have done over here is now we have changed this into a NAND gate, this into a NAND gate, and this into a NAND gate as well. Okay, and this into a NAND gate as well. So now we have this tree done. What about let's look at another AND gate over here. So this AND gate over here, I want to put a bubble like this. Okay, but remember, you cannot just put one bubble because you would change the behavior. Now you want to put a bubble in front here as well. Okay, or you can draw it this way. You can put a NOT gate over here. But remember that your system can only consist of NAND gates. So so if you put a NOT gate over here, instead of drawing a NOT gate like this, I can draw a NAND gate like this, and I connect the two input together. Okay, remember just now we did the NAND gate. This NOT gate is actually equal to AND gate. This NAND gate with the two inputs connected together. Okay, you have A, X, you have A and X. So this second one over here is behaving like a NOT gate. So this is what I'm doing over here. I'm putting one bubble over here, which turns this into a NAND gate. Now I'm also putting another NAND gate over here. This thing behaves like a NOT gate. So essentially, I'm having two bubbles. They cancel one another out. Right. So this gate done. This gate done. This gate done. This one done. Okay. Now we're left with this one. Okay. So how do you convert this into a NAND gate? Okay, we saw that the only way for you to convert this into NAND gate is to put two bubbles over here, but then you don't want to do just the two bubbles over there. You want to make sure that you cancel the bubble over there by putting a NOT gate in front. So instead of putting a NOT gate in front, I can also do this. Like I put a bar, it's like a NOT gate in front. Okay, so then this now becomes a negative OR gate, and a negative OR gate effectively is a NAND gate as well. Okay, so I have just successfully converted this circuit in red over here into a NAND gate circuit. So let's redraw this circuit with NAND gates only. So you have one NAND gate over there, and you have A, B, bar like that, and you have a second NAND gate over here. You have A, bar, and then you have B, and then you have a third NAND gate over here, that, and this one has C bar, and this one has D bar, and you also have another NAND gate over here. Like so. Okay, and you have another NAND gate over here. So it goes in here. And you have a final NAND gate over here. Okay, remember this NAND gate is connected to both inputs. Okay, so this is the example of how you convert a circuit with this expression into a circuit with NAND gates only. Okay, so now the other thing that I would like you to evaluate is the Boolean expression. Right, so we can do like let's try this Boolean expression out and see what we get. Purple. Okay, so over here we have a B bar like that, and you have NAND gates. So over here we have A bar, B, you have another NAND gate. So the expression outside here is C bar, and you have, because you have a NAND gate over there. All right, and when you arrive at here, you would have an expression like so: A, B bar, that, and then you have A. Okay, so this is the expression when you arrive at this point, and then you can do it. So here also, at this point, you would have, yeah, the expression becomes scarier and scarier because of NAND gates. But bar, A bar, B bar, you have one bar like that, and then you go through it. You go through this NAND gate, and then it's going to multiply this with the NAND gate. Okay, and finally, when you take the expression that's over here, yeah, you essentially it's repeating this 2 times with a big bar on top. Okay, so the point that I am trying to make over here is that when you arrive at this, get the expression f over here, then you get the expression of f over here, right? If you run De Morgan's theorem, you would find that this expression over here is exactly the same as this expression over here. Okay, so now you know the reason why I do not use De Morgan's theorem to convert, right? Because De Morgan's theorem, the expression in a complicated system can be very long, and it can be very mistake prone. All right, so this, however, is a good exercise, and I encourage you to try to prove it. Like the expression here and here is exactly the same. Okay, so that is how we convert a system like this, using AND gate and using OR gate, into using a system with just NAND gates. All right, any question for this one? This is the main content of our today's class. So far so good? Okay, if there's no question, then we'll just...
Yes, sir.
Okay, you have questions?
No.
Okay, all right. Okay, right, so now we can do exactly the same thing with a NOR network. Okay, the idea that I brought to you in the conversion of NAND diagrams, you can also use that idea in converting to NOR diagram. Okay, so yeah, the same idea. Okay, this is the equivalent diagram. So a NOR is actually equals to negative AND, or invert AND. NOR gate is equivalent to that. Truth table is the same. If you run De Morgan's theorem on this guy, you would get this one over here. Okay, so take a look at the diagram. NOR gate is negative N. Okay, so we can do the same procedure. Excuse me. Sorry, guys. Yeah. So we can run the same procedure over here. So what we're trying to do is, okay, so we run the conversion from OR gate first. Okay, previously we ran the conversion on AND gates first. Now with this time, we run the conversion on the OR gate first. Okay, and let's see how we do that. Okay, so let's suppose you have this expression over here, right? And you want to convert. Okay, where is my pointer? Let's just draw this expression over here, right? So this expression consists of OR gates. It consists of AND gates. Now we want the final diagram only to have NOR gates. Okay, so this is the pattern that we are looking for. So the pattern for NOR gates is the pattern of the expression looks like this: A, B, and so the output is A. Okay, so the pattern that we are looking at is something plus something, and then you have a bar on top. So take a look at the expression that we have at the output. You have something plus something with a bar on top. Okay, same thing over here, something plus something with a bar on top. Okay, so over here we have a bar on top, so it's like 0 plus something with a bar on top. And overall we also have something plus something plus something with the giant bar over on top. Right, so this is the pattern of the NOR gate pattern that we are seeing over here. So what we are trying to do is to go from this expression over here to this over here. And actually, you can do that. You can go from the left to the right by doing double negation, right? If you put the double bar on top like this, you do double negation, and guess what? You run De Morgan's theorem, and you run De Morgan's theorem, and you would get this expression over here. That is one way if you want to convert. But yeah, and I leave that to you if you want to convert it using this way. It works as well. You will get exactly the same answer. But in this example, I'm going to show you the conversion by diagram. Okay, not by equation, but by diagram. So a conversion by diagram means you need to draw it out, and then you need to start putting bubbles, and then you can get the final expression. Some of you might prefer using De Morgan's theorem. I encourage you to do both, actually. So if you can do the conversion by diagram, you want to verify that the expression is the same, put the double bar and see the same expression. If you get, then you know that your answer is correct. Okay, let's try to do this conversion by diagram over here. So let's try this one. Move this clutter over here. So we have A, B, OR gate. So we have OR gate like that. We have A, you have B, you have C like so, C, D, and they both go through AND gate. Right, and the next one we also have, so this one done, here done, this one done, and we also have to multiply it by E. Go to AND gate over here, and over here we multiply it by E. E, okay. 1 gate, 2 gates, 3 gates. Yeah, looks right to me. Let's just do a quick check. A plus B, okay. C plus D is over here, and then they both go to an AND gate. Okay, and the output goes to another AND gate with the E. Okay, looks right to me. Okay, so this is the original circuit with using OR AND gate. Now we are going to start converting this into universal gates using conversion by diagram. So as with the previous example, what we want to do is to try to add bubbles, but we want to make sure these bubbles cancel one another out. So previously we started with AND gates, right? And now this time we're going to start with OR gates. So we're going to start putting this one. Now this one is a NOR gate already, and we're going to put a bubble over here, bubble here, and here. So this one is a NOR gate. This one is a NOR gate. This one is also a NOR gate. Now what about this? So we want to put, so you want to put here a NOR gate. So you want to put this one here, and you put a bar here, and you want to put here, and you want in between here, you got to put a NOT gate over here. So you want to put a NOT gate over here in between, like so. And this NOT gate, you can redraw it using NOR gate. So how do you do that? Let's take a look at how do you draw. Yeah, so this is a NOR gate, and it's behaving like a NOT gate if we connect the two inputs. Okay, that is how we are going to draw this circuit. Okay, if you connect two inputs, then it is behaving like a NOT gate. So let me just draw cute NOR gate like this, two inputs connected, and all right. So this is the conversion by diagram. So now, once you're done with the conversion by diagram, verify that they are all NOR gates. This is NOR gate, NOR gate, NOR gate. They are all NOR gates over here, and this one is also a NOR gate. And verify also that all bubbles actually cancel one another out. One, here, here. So you have a NOT gate here, and you have a NOT gate here, and you have NOT over here, NOT over here. Okay, so it looks like this conversion is okay. So let's try to see. Let's try to redraw this. Okay, redraw this like that, like that. Okay. So we have A, B. This is NOR gate number 1. This is NOR gate number 2. C. Then you have D. And then this is another NOR gate, like so. And then you go to a NOT gate. So a NOT gate, like so. Okay, but you need to connect the two inputs. And finally, you go to another NOR gate, like so. And this NOR gate is connected to E bar. Okay. So what we are seeing over here. So let's try to evaluate the expression. Okay. So what we have over here is actually this expression. Okay, this expression over here. We see over here that this is actually at this point. This one, the second C, is actually at this point, and then E. You can see that this is everything. E is actually at this point. Okay, so let me just not make this too messy, right? So what I'm trying to say over here is the expression F is exactly what you have over here. Okay, and are they equivalent? Yes, they're equivalent. You can prove it using De Morgan's theorem. Okay, so that is how we do the conversion from a usual OR AND circuit, and you convert it into a circuit only with a NOR gate. All right, that will be yeah, I think that will be my last slide for today. Any question before we end our class today?
No, sir.
Okay, so this will be your attendance again today in case if you came in late. So today's class, as usual, we'll have like a quiz as well, following up on what the content that we've covered in today's class. Like talking about your quiz, right? I've marked a couple of your quizzes, and I've returned them to you, right? I'm not sure if you guys are aware. I wrote comments in the return for each questions. So if you know that, do check this out, these comments out, because I noticed that some of you are not checking it out because I told you to do something in the comments, but it's happening again in your next quiz. So do check out these comments. Like if you have your the marks taken away, I usually will explain them in the comments, how you can do to make it better. And if you have any questions, you can let me know. All right. And also, I ask that for, let's say the quiz asks for question A, right? When you submit your answer, only put your answer for question A. Like don't put all the questions as your answer for question A. Okay, let's say there's 4 questions, right? And there's like 4 separate submission, 4 separate uploads that you need to do. So don't take everything and then put it into the answer for the question, because you know what? Because if you put in everything as the answer, now I will need to search through everything to see which one is your answer exactly. And because I have many students and sometimes mistakes can happen over there. So I would like to really ask of your consideration to only submit the answer for that particular question, for not for other questions. Okay, so that will make the marking, my marking at least, quickly and with less mistakes. So this is what I hope you guys will do. And if you guys are not using the document scanner, please use the document scanner, because in some of your answers, I can hardly see clearly using your phone camera, right? So do use that document scanner. Okay, if there is no other questions, then I will see you guys again next week. And if you have any questions, please feel free to stay back and I will answer your queries. All right, have a good weekend, guys. I'll see you. Take care.
Thank you, sir. Thank you, sir.
All right.
Hello, sir.
Hi, hello.
Can I ask a question? But regarding assignment 4,
Yes.
I'm Shamian. I asked previously about question assignment 4, question 1. Does the answer really is 0, sir? Does it mean that for question 1, if the simplified SOP form is 0, does it mean that there is no logic diagram for the simplified form? Just confused about how to answer that question.
Oh, yeah. I think I haven't gone through exactly your question, but yeah, there is one a question that evaluates to 0 at the end of the day. So
Ah.
0 means yeah, there was one. So 0 means that you give whatever input, the output will always be 0. That's how you want to see it, right? So yeah.
Okay, so the answer can be 0.
Yeah, of course, the answer can be 0. So that is kind of like a trick question, actually. So some of you like might be confused. Why is the answer 0, right? Yeah. So you can simplify. Yeah, you can simplify that equation into like actually this equation evaluates to 0, which means that whatever input combination that you give, it will always give you an output of 0. That is what it means.
Okay.
Yeah.
Okay, sir.
All right.
Thank you.
Okay.